So let's look at a few integration examples where we actually do use partial fractions. So here's our first example. We have 1 over x squared minus 5x plus 6. Now typically on a problem that looks like this we would try to use some kind of a u substitution, but you'll notice that if we let u equal this denominator, then du would be 2x minus 5, and in the numerator we only have a 1, so it doesn't really work that way for us. We could complete the square in this denominator and use trigonometric substitution. That's not something that we cover in AB, and it's not that much fun. So it's much easier to use partial fractions for this problem. So clearly this would factor into x minus 3, x minus 2. So if we do that, we're trying to split this up into something over x minus 3 plus something over x minus 2. So I'm going to use the cover-up method here to find the partial fractions here. So I'm going to look for the numerator that goes with x minus 3. I'm going to let x equal 3. So I have 1 over 3 minus 2 is 1 over 1 is 1. All right, when I cover up the x minus 2, I'm looking for the numerator for the x minus 2 term. So I let x equal 2. I have 1 over 2 minus 3, 1 over negative 1 is negative 1. So what I really have is just this. 1 over x minus 3, I have plus negative 1 over x minus 2, I made that a minus 1 over x minus 2. And when I integrate each of these, I can think of it as using u substitution. U equals x minus 3, du equals just dx. Here u equals x minus 2, du equals dx. So these are both just natural logs. So I have natural log of absolute value of x minus 3 minus natural log of absolute value of x minus 2 plus c. I'm done. All right, and that is a lot easier than using trigonometric substitution on this after we complete the squaring for sure. Okay, so that's the most basic type. You'll notice here that the denominator has a higher power of x than the numerator did. Just like any other problem that we've seen all year, if we start with a numerator that has a higher power than the denominator, the first thing we're going to use is polynomial long division, and then the rational expression part of what's left, we'll use partial fractions on that. All right, so the example that we're going to look at here looks like this. Pretty complicated thing. Notice that the power of x up here is higher than the power of x in the denominator. So the very first thing we're going to do is polynomial long division. All right, so I'm going to come over here. We're going to do this division. Zoom in a little bit on this. So when I do polynomial long division, I list out all the terms. Here I have a power of x. I have a term for each power of x, so I don't have to have any placeholders or anything. I have x cubed, x squared, x, and the constant. I write the numerator here, and I'm going to divide leading terms. So I'm going to go 2x cubed minus x squared. I get 2x. I'm going to line that up over the x term there. Now I'm going to multiply this down. So I have 2x times x squared, 2x cubed, 2x times 5x, 10x squared. And notice that I'm lining them up under the appropriate powers of x. 2x times 6, 12x. Now I subtract. The leading term should always cancel out. That's how I got that answer up here in the first place, was dividing by the leading terms. So that should always cancel out. 13 minus 10x squared is 3x squared. 27x minus 12x, I get 15x, and I'm going to bring down the 16. Now I'm going to divide again. I have 3x squared divided by x squared. So again, I'm just dividing the leading terms. So I get 3, and then I multiply down. 3x squared. I get plus 15x. Now 3 times 3 times 6 is 18. When I subtract, in this case, these two terms both cancel out. So I have minus 2. So what I'm left with is I have 2x plus 3 plus a negative 2 over x squared plus 5x plus 6 when I do that polynomial long division. Right? So I'm left with now trying to integrate this. All right. These are going to be very easy to integrate. This is just polynomial in x. Here I have now something that I can use partial fractions on. All right, so I have a quadratic denominator which can factor. It'll factor into x plus 2, x plus 3. So we're going to come back over here. I'm going to do the partial fractions. Sorry. Again, I'm going to use a cover-up method here. So I want the numerator that goes with the x plus 2. I'm going to cover up the x plus 2 and let x equal negative 2. So when I do that, I have negative 2 over negative 2 plus 3 is 1. So I get negative 2 there. And then for x plus 3, I'm going to cover that over and I'm going to let x equal negative 3. So I have negative 2 over negative 3 plus 2, negative 2 over negative 1. That's a positive 2. So this expression, negative 2 over x plus 2, x plus 3, is equal to negative 2 over x plus 2 plus 2 over x plus 3. So once I do the partial fraction decomposition there, now I'm trying to integrate this. There's 4 terms here. The first 2 terms integrate really easily. Antiderivative of 2x is x squared. Antiderivative of 3 is 3x. Here I have another linear denominator and another linear denominator. So I have negative 2 ln of absolute value of x plus 2 plus 2 natural log of absolute value of x plus 3 plus my plus c. Alright, so that's an example where I start off with a higher power of x in the numerator than in the denominator, but I notice that I have a factorable quadratic in the denominator. So I do the long division, get it in terms of some polynomial plus a rational expression with that same quadratic denominator, then use partial fractions on that denominator, or I'm sorry, on that expression, and then I can integrate each part really easily from there.